Okay, shall we get started? Okay, the voice still works. Okay, welcome everybody to set theory in Master Math. I was a bit worried because there are 66 students on the ELO and only 40 chairs in this room. And one set theoretic principle, the pigeonhole principle, tells us that gives us a problem. It looks like there's still one chair available. So I wonder what happened to the other half of the population. Okay, all kidding aside, nice to see at least a full room. So what is going to happen this semester? Well, I'm going to tell you about set theory. The first half I will do the, say, axiomatic foundations of set theory. So today will be a little bit of history, and then I will tell you about Zermelo's axioms. And then next week we'll do it once more, but then for real. And I have something to say about that as well, why for real. And then we'll build up set theory according to the axioms, see what we can do. And so halfway through the semester, we will have seen that all of mathematics, normal mathematics, can be done inside set theory. Some category theory needs a little bit extra work, but anything that you've seen in your first 2 years or so can be formalized within set theory, and that makes it, to many people, the foundation of mathematics. You can agree with that or not, but I do. Doesn't mean that if you disagree, that'll dock you a point at the exam, but it's just one of the foundations, and as I said, it's most accepted by very many people. That's one thing, and after that, I will do some combinatorial set theory, some real fancy set theoretic stuff that can be used in all kinds of disciplines. And the final bit of the course will be this year's special topic, and this year's special topic will be the constructible universe, Gödel's constructible universe, which is about 80 years old now, which he used to prove, finally, the consistency of the axiom of choice and the generalized continuum hypothesis. People have been using those freely in their work, but Gödel actually showed, well, you don't get into trouble when you do that. That's roughly the schedule. The practicalities are, okay, last year there were 2 of us with 2 teaching assistants. This year it's only me. I will hand out homework bi-weekly, as you can see on the ELO. So every 2 weeks I will give you some exercises to do. You can hand them in, I'll mark them. Lots of red ink to show where you all went wrong or where you did really well. And that will count 20% towards the final grade. Now, apparently, some people kind of misread what is on the ELO. Let me explain. Master Math says if your exam grade is less than 5.0, you don't get a passing grade, and actually we don't actually give a grade, but some institutes do accept failing grades, so we'll communicate them. But if you score 4.9 or less, well, less than 5.0 at the final exam, that will be your final grade, no matter how well you did your homework. If you have 5.0 or more, then I will take the maximum of the exam grade and 80% of the exam grade plus 20% of the homework, whichever is larger. So the homework can only raise your grade a little bit. And that is why I wrote on the ELO, it is based on, it's not 20% homework, 80% final grade. There is this proviso by the rules of Master Math. But anyway, if you do your homework quite well, it'll help to raise your grade a little bit. I think those are basically, I like to keep these kinds of things simple. Last year, my colleague managed to fill half an hour with all kinds of things that could be going on or not. Although that was a different situation. We did it online and we had to take care of a few other things. And now you can simply ask me when I'm here and things will be solved quite quickly. Okay, any questions from your part about, say, the practical goings on in the course?
Apart from the books in the Mastermind page, do we have lecture notes from previous years? Something?
There is a sentence just above the books that I put in a few days ago. When I prepare, I write notes in a notebook, and I will scan those and put them on the ELO tonight. And the sentence on the ELO says, and this will automatically determine the contents of the course. And the books are very much recommended, but you can treat them as background material. Maybe occasionally I will steal one or two problems from the books, but then I will retype them and put them in a separate file or something like that. There is hardly any originality in the homework. Everything is stolen from other sources, commonly. So, yeah. So like I said, I will scan those. They will be on the ELO tonight, because I didn't scan them before. I don't know how far I'll get, and how far I'll get. That is what I'll put on the ELO. Yeah, about those books. I actually saw this already lying around there somewhere. This is Jech's set theory, the third millennium edition, and which was quite a thing 20 years ago, but now everybody, well, the third millennium, it's almost over. And this is Koenen's set theory, an introduction to independence proofs. And as you can see, it's very well thumbed. I used it a lot. I learned from that. Those are my favorite books to read up on set theory from. Koenen really explains many things very well. Also the philosophical side of set theory. Jech is more encyclopedic, shall we say. Not all the proofs are really complete, but there are plenty of references. So you can, yeah, like I said, you can sort of use Jech's book if you're really seriously getting into set theory as sort of the basic reference. If you need to know something, you look it up in Jech and you'll find other references to other papers where you can find more.
So is it Jech or Jech?
Neither, Jech.
Jech.
Yeah. Well, he's from the Czech Republic, or Czechoslovakia as it was then. So it's the soft ch. But he lived in the US for a while, so I guess everybody over there called him Jech. But it is the as in München, and the German CH is quite a good approximation. And well, Koenen is Ken Koenen, everybody knows. Well, unfortunately, he died a few years ago. He was a very, very, very nice and very clever guy, but alas. Okay, so, I would like to know who from the 66 is really here. So just put your name, no email address or whatever is necessary. Maybe not name and institute. Numbers I'll get in one Excel sheet or whatever. But on the ELO, I cannot see where you're from. Unless you use the university email address, of course. Well, if it's John Jones at uva.nl, chances are you study here. Okay, so I said I would start with a little bit of history, but we'll do a little bit of mathematics anyway. Oh, I forgot, but you probably know that from the ELO. My name is Hart, and it's quite easy then to turn that into an email address. This is the email address from the university in Delft. So I'm a general topologist and I dabble in set theory too. And for some reason, since about 10 years I've been doing this at Mastermath now. Okay, I'm going to write two very long definitions on the board. And so you'll have to bear with me for a bit. This date is not precise. I will say something about that in a moment. Whoops. So it's going to be it's German, so it's bound to be a mouthful. Okay, there is something in parentheses that you will find in my notes, but I'm not going to copy it down because it just clarifies what he says over here. Okay, this is Bernard Bolzano, also from the Czech Kingdom when he was born, and it was part of the Austrian Empire when he died. So again, you can visit the place where he lived in, well, not visit, there's a plaque in Prague where you can see where he lived. He was a priest, but he also did mathematics, and he did a few things before anybody thought of them, but because of the publication mores in those days, people didn't know he did. He was the first to define a continuous function that was nowhere differentiable. And he was the first to really, almost really prove the intermediate value theorem. He knew that it was necessary to prove it. Not saying function is continuous, see if you draw the graph, it has a zero. No, really, analytic. And he thought about the infinity. I hope I spelled that right. Yes. So the paradoxes of the infinite, he was thinking about the infinite. He didn't agree with the old Greeks and with Gauss and other people that there was no actual infinity. He believed, yes, there is a completed infinity available somewhere. And he had all kinds of reasons why, and I'll put your mind at ease, it has been translated into English. So if your German is not that fine, you can read the English version of it. And it's nice. It's nice to read it. But anyway, so here a thing, an inbegrif. I'm not quite sure how to translate into English. Where we sort of understand that the ordering is not important, we call a set. Well, the ordering, you have to think, he probably wrote this earlier. This was published after his death, by the way. He was thinking about sets, about the infinity or whatever. And at one point, he needed to have the idea of a set, of a menge. And he wondered how to formulate that. Now, if you think of what people were thinking about in the beginning of the 19th century and also through the whole 19th century, usually the real line, the plane, three space, after Riemann also many more dimensional spaces. So things happened in the real line, they happened in the plane, they happened in three space and everything. So they came with an order, they came with all kinds of mutual relations. And what Bolzano said, well, if we don't look at all those relations, just look at the individuals we have, then we call it a set. Otherwise, we call it something else. So one of his examples was a glass. I mean, a glass that you drink from. He said, well, if I break it, it's still the same set. Some of the molecules might have flown away, but it's still the same set because the relation between the molecules, well, I don't know if he knew about molecules at that time, but the relation between the constituents is not important if I think of it as a set. That was his example. He also was thinking a little bit about bijections. He had, for example, but I always wonder why 5 and 12. I would simply do 1 and 2, but he said, well, you can put these two into one-to-one correspondence, but this is really smaller than that. Because it's an initial segment of it. It's okay, something was going on, but he didn't pursue that any further. You know, of course, that in the elements, Euclid says that the whole of the part is smaller than the whole. And here is a part that you can say is the same size as the whole. A bit weird, maybe in those days, but Bolzano simply observed it and he let it pass. Okay, so Cantor used quotation marks. These were the old German quotation marks. There's something nice about this definition that we'll talk about in a moment, but something is already happening here. So a set, by a set I mean a collection, any synonym you would want to take of collection, set, whatever. This is a long word. there are two things happening here already. We have sort of variables or constants. So by a set, I mean a collection, shall we say, collective or whatever, M of certain objects, distinguishable objects, and they were given a name too, little m. Okay, there's a little bit in parentheses here where he says I call them the elements of M. Okay, I don't have enough room here. There was a little bit more. So I'll just write the English word notation here. So this is slightly different. By a set, I mean a collective, a collection, M of certain distinguishable objects, M of our Anschauung, what do you say, the consideration, or our thinking, into a whole. And in the German it says, im Zeichen drücken wir das so aus, M is equal to, so we already have the curly braces here. And we have the word element, it could be found here in parentheses. These were two attempts at defining what a set is going to be. Bolzano had an idea, Cantor had an idea. By the way, this was 20 years after Cantor started developing set theory. Next year, December, will be 150 years that the real line is uncountable. The 7th of December. We have the date of the letter where Cantor gave a proof. So this year you'll have to make do with 149. Anyway, in 1873 he proved that. He proved many other things. He started his investigation, and in 1895 he wrote a big two-part paper where he sort of collected everything he had done so far. And one of the things he needed to do was define what he was talking about, set. And when you look at this, it looks pretty impressive, especially in German, but it's full of synonyms. Because Zusammenfassung, einem Ganzen, we collect things into a whole, and that whole is the set, and the collection is the, yeah, well, right. For us, in the dictionary, when you look up set, you'll find that it is a collection. When you look up collection, you'll find something else, and eventually you get back to set. So we don't really get very far if we try to define sets in that particular way. In mathematics, we usually define something in terms of something else. And at some point, there's going to be a moment where you don't define anything. You simply say, oh, this is what it's going to do. And that is what we'll be doing in the coming weeks. Not really define what sets are, but describe their behavior. Now, but this is generally the way we think of sets. If we look at an interval in the real line, it is the Zusammenfassung of some points that sit between the A and the B, and we collect them into a whole, and that interval is a set. So it's what we do, naively, so to speak. But this is quite general, and even Cantor, because of all his investigations, here are a few of those Zusammenfassungen, a few of those collections. We'll define ordinal numbers later if you haven't seen those before, and cardinal numbers too. But when Cantor started working on his set theory, these are two of the notions that he defined, and he used them and he knew what to do with them. So they were there. Well, the set of all sets, what's wrong with that? Well, one of the things that Cantor proved, and we'll see it too, and maybe you've seen it already, if you take an arbitrary set, then you can find an injection into its power set, but you cannot find a bijection. So the power set really has essentially more elements than the set itself. If you have a club, you can make way more committees than you have members of your club. Now, look at the set of all sets. The problem with the set of all sets is that its power set is a subset of it, because it contains all sets. And yet, we have this. Oops, you would say. Same thing with the ordinal numbers. If you define them properly, then if the ordinal numbers form a set, they determine an ordinal number that has to be smaller than itself because it's among the ordinal numbers. Okay, and the same thing happens for the cardinal numbers. That's a bit okay, that's unfortunate because the problem was set theory turned out to be very useful. As soon as Cantor opened the floodgates of set theory, many people started to use it, and without the idea of set theory, we wouldn't have had Lebesgue measure, for example. Because if you want to formulate that in a nice way, you need to talk about sets and whatnot. And also functional analysis, although it was in its infancy at that point, the set of all functions from A to B or whatever, you need to talk about that. And Cantor gave us the language to do that. So everybody, well, set theory, great thing. Ooh, that's not very nice. Okay, Cantor's idea, when Cantor found this one, the cardinal numbers, that was Cantor's own paradox. He says there's something fishy going on there. Cantor started to talk about proper sets, real sets, and not quite sets, improper sets. And these things were improper sets. They looked like sets, but they weren't really. That doesn't sound very mathematical in my ears anyway, but actually, when we do into the course, we will actually find what those improper sets can do for us, because they can be useful. And instead of improper sets, we call them classes. But we'll meet them later on. So anyway, something was wrong. Well, what was wrong? This was all done in words. And the words, can be a little bit slippery. And so Frege, at the end of the 19th century, said, well, use formulas to describe them. And, okay, it's a bit anachronistic because I'm not quite doing it the way Frege did it. You take a formula in the language of set theory, call it F, and you collect all the x's that satisfy that formula. And that is sort of the formalization of what Cantor said. If we let our thinking and our consideration be guided by nice formulas, then maybe things will be okay. Well, not really. You can write down nice formulas that will describe all sets. Namely, all the things that are equal to themselves, those are the sets, all the sets. There is a formula for ordinal number. You write it down, and then that would be a set after all. So still, we would have the proper and improper sets. Now, there is one thing that these three have in common. They're pretty big. Humongous, I would almost say. The collection, the universe, whatever you want to call this, of all sets, everything is in there, so that must be pretty big. The ordinal numbers keep going on forever, way longer than the natural numbers or whatever you want to consider. The same with the cardinal numbers, as we shall see. So these things are really pretty big. And that was one of the solutions that even Cantor advocated. Okay, a set is something that is set-ish, but it's also small, whatever that may mean. So small that it's not as big as those things. Yeah, okay. Well, that went out the window. That went out the window when Russell thought about it. Russell got Frege's book. Frege was writing 2 volumes about the foundations of mathematics. And somewhere in the first volume, Russell found something akin to this is always a set. Not quite the same thing, but roughly. And he started to think about it. He said, well, wait a minute. What happens now? Well, actually, Russell came to this by looking at the proof of this. He said, well, okay, well, in that proof, you actually do something like this. Okay, interesting. Well, let's look at this and put it into Frege's idea. It's a bit, why won't this go on more? You get a very simple logical contradiction. If that thing happens to define a set, then that set is a member of itself if and only if it isn't. That has got nothing to do with size. We just say, well, we have a simple formula. I mean, it does. The simplest one is x is an element of x. The next simplest one is the negation of that. We have a very simple formula. It doesn't even define a set. Yeah.
So how did Frege rule out putting x equals x for f here, or did he?
He didn't. No, like I said, this is akin to what Frege did. I'm translating it into set theoretical. So you have to read Frege's book, because the first book was all about arithmetic, and the rest came later. So, like I said, this is analogous to what Frege was doing, and I think, what was it? It was more of the nature of properties that could also be, say, semantic in language or whatever. And I think one of the forms is the heterological, what's the converse of the...
Homological? Homological?
No, it's heterological if it doesn't apply to itself, and it's autological if it does apply to itself. And so what is heterological? Well, is it autological? No, it doesn't apply to itself. Is it heterological? Well, it does apply to itself, and there's the contradiction. And Frege was talking about that type of notion. And Russell found an analog of this in that case as well. Maybe not the heterological tautological paradox, but something similar. So anyway, there you go. If you try to do this, you're stuck. You have a problem. So people figured out that one should be careful. So I simply started to read Zermelo's paper, and I thought, oh, that's nice. Let's talk about it tomorrow. So that's what I'm going to do. And we're going to need that material anyway. But it's nice to see how Zermelo worked with it. Okay, so it was 1908. Yeah, if I'm not... I put a link to that paper on the ELO, by the way. So you click on it and you get to... It was 15, 20 years ago, so in Germany they started to digitize almost everything, and all the work of Cantor and Zermelo and all the other guys from the 19th and 20th century is online, available there. Wonderful resources. Anyway, Zermelo's paper is there. When you read it, you'll see that he talks about the contradictions that arose, especially the Russell one. That made set theory a bit troublesome. So what are we going to do? And Zermelo said we need some principles, some axioms to start us on our way. Not quite the way you may have seen this in your first order logic courses, but close. So, where were we? Yeah. He started with okay, these things were undefined, but not objects. Those were. If you try to do this in normal speaking language, things are going to go wrong. Because we have a domain that consists of objects, and we call the objects things, right? That's simply using another word, another synonymous word to describe your things. And our sets so every set is a thing. Lovely. Okay, the domain. Although I don't think the domain is the 100% precise translation of Bereich. That's why it's called B and not a D. But anyway, for me, domain is good enough. If we say that something exists, it means that it belongs. Okay, I intend, that's one of the practicalities I didn't mean. I intend to talk for about 45 minutes, then we have a break, and then 45 minutes again, and so on. That's the periodicity here. So I still have a few minutes, and then in the next hour we'll talk about the rules governing these things. If something belongs to B, then it exists. If it doesn't belong to B, we don't look at it. It doesn't exist for us. We have a relation. Again, sort of used by synonymity, but A belongs to B is what we usually then we say we abbreviate it like so, and now it's suddenly we say, well, this is the thing, and it means that. Anybody know what letter this is?
Epsilon? Is that epsilon?
Well, okay, originally an E. Because Peano, an Italian, invented this, and it simply means E means is, and so in Italian it says A is a B, and so the B is the sort of things that it is, and A is of the sort B, so to speak. You didn't know you would learn languages too here. Okay, the word element is brought into play here as well, but I'm not going to copy that now. Very carefully, a thing that contains an element, A, can be called a set. Not everything that contains an element is going to be a set, as we will see, but it can be. And then you say, well, we all know the empty set. With one exception to be seen later. And let's see, so okay, it's 1:45, so let's stop here and we'll go on with this. Let's at 3 o'clock we'll reconvene. So this is the domain of discourse that Zermelo is going to work in. And here is, okay, something can be a set, but it must have an element. Okay, with one exception, and we'll come back to that in a moment. And that's it. Notice, and this is the last thing I'll say, it says a relation. It doesn't necessarily mean that this B is a set in our way of thinking, and that A is actually among the elements that we see in that little box B. This can simply be any relation on the domain B. And so last year, when Benedict Leu was still doing this, he spent some time on the model theory of set theory. And the model theory of set theory is actually directed graphs. You draw any directed graph that is a model of this. And using those directed graphs, you can figure out why certain axioms cannot be derived from other axioms and such. But even Zermelo already, when he starts to talk about it, it's obvious that he's thinking about sets with curly braces around them. But he is careful. It's just a relation. That we are going to interpret it as, yeah, well, this is really in the box with label B. That's our problem. Okay, we'll continue at 3 o'clock.